Good afternoon, everyone. I'm Sheenam, and it's a pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's insightful webinar on automotive acoustics and COMSOL multiphysics. We are delighted to have you join us today. To begin, we would like to extend our sincere gratitude to our partner COMSOL for their continued support and collaboration in making this session possible. Before we dive into the session, I am pleased to introduce you our esteemed expert speaker for today, Ms. Kavita K. She is an application specialist at COMSOL Multiphysics Private Limited. She has worked on advanced research projects at Raman Research Institute, where she was involved in the design and analysis of frequency independent antennas for cosmological experiments in radio astronomy. At COMSOL, Kavita specializes in electromagnetics and acoustic wave propagation, supporting customers with multiphysics modeling across MEMS and real-world engineering applications. We are delighted to have her with us today. Now, to give you a brief of today's session, automotive acoustics play a critical role in model vehicle design. It encompasses the analysis of vibration and noise in mechanical components, optimization of ultrasonic sensors for parking and safety systems, development of advanced automotive audio for precise sound reproduction, and integration of smart systems with AI-enhanced functionality. This multidisciplinary field brings together acoustics, structural mechanics, electromagnetics, and fluid dynamics to model, analyze, and optimize key vehicle components, ultimately enhancing both vehicle performance and passenger comfort. In today's webinar, Ms. Kavita will demonstrate how COMSOL multiphysics can be used to model and analyze a range of automotive acoustic phenomena. The session will cover broadband cabin acoustics with integrated audio systems, acoustic packagings using absorbers and damping layers, electroacoustic speaker design tailored for automotive applications. Following the presentation, we will move to a live Q&A session where Ms. Kavita will address questions submitted through Q&A box. Please feel free to share your questions at any point during the session. We will also be launching poll questions during the webinar. We encourage all of you to participate and share your responses as this helps make the session more interactive and engaging. With that, it's my pleasure to hand over the session to our speaker, Ms. Kavita. The floor is all yours.
Hello everyone, greetings from COMSOL team. I'm Kavita and I extend my warm appreciation to everyone participating in this webinar on modeling and analyzing automotive acoustics applications using COMSOL multiphysics. Today, we will be discussing a wide range of applications in acoustics relevant to the automotive industry. So this includes analysis of the vibration and noise in mechanical components, optimization of ultrasonic sensors for parking and safety. It can be related to the development and analysis of advanced car audio systems and more. So when we talk about automotive acoustics, it is a multidisciplinary field where you would require to merge acoustics, structural mechanics, electromagnetics, and fluid dynamics in a single simulation to model and optimize key components, which is essential for the vehicle performance, and also to enhance the passenger experience, which is our prime interest. And hence, COMSOL Multiphysics stands as one of the best platforms here, as it provides you a single graphical user interface platform where you can couple multiple physics to model a real-life product or problem. So moving forward, before beginning the session, I would like to raise a poll question here. So to understand about your background on usage of simulation tools, we would like to know whether you are a regular user of simulation tools or you are evaluating simulation tools for your ongoing or upcoming project, or you are attending the session out of your personal interest, or you use simulation tools, but you are new to multiphysics simulation. So we would like to know the background of view on usage of simulation tools for automotive acoustic applications. Kindly take time to answer this poll question. Yeah. Thank you for taking time to answer the poll question. To start with, automotive acoustic applications can fall under three different groups, which are listed here. Towards the left is the sound that we are not usually interested in hearing, which is the noise and vibrations. In analyzing noise and vibrations, you would predominantly model the coupling between acoustics and solid mechanics. So, and the type of noise can be powertrain noise, aerodynamic noise, rattle noise, or tire noise. The second group is where you analyze the sound which we are interested in listening and optimizing it for better experience. So this is about the car cabin acoustics and optimization of the stereo systems inside the car cabin. And you can also model the acoustics of the environment and the personal sound zones as well. And you can also model voice control smart systems as well. Finally, we have the sound groups, which we do not hear, which is on modeling sensors. It can be ultrasonic parking sensor or surface acoustic waves, SAW-based tire pressure sensors, etc. So before moving further, I would like to know the application areas of interest. So basically the application that you work on, whether you work on motor and gearbox noise, or duct acoustics and HVAC noise, or you work on car cabin acoustics, or you work on sound absorbing materials that are used for damping, or if it is any other application areas, you can mention the application areas in the questions tab. So I would request you to kindly take time to answer this poll question as well. So this poll question will help us to understand your application areas of interest. I would request Ms. Sheenam to kindly launch this poll question. So this will help us understand your application area of interest, and we can take the session further accordingly. Yeah, thank you for answering the poll question. And we could see that, we have a good interest in analyzing the vibroacoustic problems, basically in understanding noise and vibrations, and also modeling car cabin acoustics and electroacoustic models as well. Thank you. So, here what you see in this slide are the solutions that COMSOL Multiphysics has to address the automotive acoustic applications. Most of the applications are multiphysics in nature, and many of the problems require vibroacoustics in modeling the acoustic structure interaction, where you model the elastic waves in solid and the pressure waves in fluid, and you need to couple the interaction between the two. So the noise here can be a structure-borne noise, or it can be a vibration-induced noise as well. And when you are modeling these type of problems, vibroacoustic problems, so you might require to model porous material, which are widely used to reduce noise. It can be porous materials to model the floor carpets or roof linings, seats or door panels of your car or vehicle. It can be used in mufflers and particulate filters as well. So you can see an example here, screenshot of an example of an absorptive muffler. So which also uses a porous domain. A glass wool is used as a porous domain here to reduce noise. And another important topic where you have to capture multiphysics is electroacoustics. So this is required for loudspeaker design and car cabin acoustics to study the response of your real speaker sources. And piezoelectricity is another phenomena that has to be captured to model ultrasonic sensors or transducers in detail. Here, COMSOL provides solution for all these multiphysics phenomena using its ready-made multiphysics couplings. And also COMSOL offers range of numerical methods that can be used alone or it can be combined together to meet specific needs. So here you see few of the listed methods which COMSOL uses for acoustic applications. It is primarily based on finite element method, but when you are modeling very large acoustic problems, acoustic radiation or scattering problems, you can also use boundary element method. And you have ray tracing to model acoustic wave propagation over very large distances. And for time domain simulation to accelerate the simulation. So you also have time explicit discontinuous Gallatin method as well. So now let's move on to take a closer look at these multiphysics and the multi-method approach. So for modeling a vibroacoustic problem, we require modeling of the structural vibrations, which can be performed using solid mechanics or shell if you're modeling the structure as thin structure, or it can be a multi-body dynamic system. Then thereafter you require modeling of the acoustics in the fluid, and you have pressure acoustics, which is based on finite element method or boundary element method. And COMSOL provides you the built-in features to couple them. Next, we need to couple them. So we add structural mechanics, we add acoustics, we need to couple them to capture vibroacoustics. So here you see a screenshot of a part of COMSOL GUI, which shows the modeling workflow for setting up a vibroacoustic problems. So this particular model involves acoustics in frequency domain, boundary element method, basically a finite element method and boundary element method, and you also have structural mechanics physics. So, and you also see a multiphysics node here, so which captures the coupling between your acoustic physics and structural mechanics physics. So you see the multiphysics coupling acoustic structure boundary interaction. So which couples the acoustic physics and structural physics, solid mechanics physics, to capture the acoustic structure interaction. So moving on, we have an example here on electric motor noise from COMSOL's application library. The sound we hear from an electric powered machine is a multiphysics phenomena. And as the motor's electromagnetic activity sends vibration through both the machine as well as the surrounding air. So here COMSOL multiphysics, through COMSOL multiphysics platform, you can simulate the acoustical effects generated by this permanent magnet synchronous motor, which is shown here, at different speeds of rotation. 3 studies are performed here to analyze this model. The first study is a transient analysis to determine the electromagnetic forces in the frequency, in the time domain for a given speed of rotation. So we do a time domain analysis to understand the electromagnetic forces for a given speed of rotation. Then a Fourier transform is done to convert the time domain forces into different harmonics in the frequency domain. Because the frequency domain analysis allows you to efficiently compute the vibrations and noise in the 3D model. And further at the end, a vibroacoustic analysis is done at each harmonic and varying speeds of rotation. And you can plot the acoustic radiation as well at different distances. So here at the right topmost end, you can see the acoustic radiation out from this electric motor. So operating at different speeds of rotation, so you can plot the acoustic radiations. Here we have another complex model from COMSOL's application library, which is gearbox vibration noise. So the gears they are used in variety of applications. So gears can be used for clocks, industrial machinery, music boxes, or automobiles. and they are a major source of vibration and noise irrespective of how it is going to be used. The most effective approach to reduce the noise radiation from a gearbox is basically to perform a vibroacoustic analysis to improve the design. So here, in order to numerically simulate the entire phenomena of gearbox vibration and noise, we perform two analyses. So first is the multi-body dynamics analysis to model this gearbox mechanism. Then the acoustic analysis to understand the noise out from this vibrating gearbox device. So in the multi-body analysis, we compute the dynamics of the gears and housing vibrations. And this is performed at different specified engine speed, and the output torque is analyzed in the time domain. And further, the normal acceleration of the gearbox housing is converted to frequency domain, and that is used as a noise source for your acoustic analysis. So for the acoustic analysis, we compute the sound pressure level outside the gearbox for a wide range of frequencies. So using normal acceleration on the housing of this gearbox as the source of noise. So moving ahead, next we have the example of fuel tank vibration. So this is another model that analyzes the frequency response of a fuel tank partially filled with fluid, again on vibroacoustics. Here the tank is submitted to a vertical acceleration, and two modeling methods are considered to represent the fluid here in the tank. One is the traditional added mass approach versus the fully coupled vibroacoustics approach. And here in the plot that you see here at the top rightmost end, the two methods show significant differences. And it also highlights how it is very important to accurately capture the vibroacoustic behavior when you are going to predict the stress or fatigue life on fuel-filled cavities. So moving on, you can also simulate mufflers, particulate filters by coupling acoustics with fluid dynamics and structural mechanics, analyzing phenomena like pressure wave propagation. You can analyze the acoustic damping in your porous material, or to study the shell vibration that are going to affect the noise reduction or noise reduction mechanisms that you're going to take to improve your design. So these simulation will help engineers to optimize the design by understanding how the acoustic damping or the material properties and the physical structure of the mufflers and the diesel particulate filters, how they're going to interact to control engine noise and emissions. So these are various models from COMSOL application library, and we will also see one of the model in our demo session on absorptive mufflers. Yeah. To start with, we will look into the problem of, so we saw already the problem of noise and vibration. So next we will move into the problem category of modeling sensors. So we will go through the modeling approach for modeling ultrasonic car parking sensor. So here you see the example of this ultrasonic car parking sensor, which demonstrate how you can model ultrasonic transducer as a standalone component. So here you see the ultrasonic transducer model as a standalone component, and use the results of that to define a source in a very large scale model of the propagation to understand the propagation of the sound. So this is basically the large scale model is solved using ray tracing approach. So you analyze the transducer or design the transducer in detail in finite element method, and you place the transducer on a very large geometry and analyze the propagation of sound over very large distances using the ray tracing approach. And for modeling the transducer in detail, what all is used in this particular model is the piezoelectricity multiphysics coupling to model the transducer mechanism, and acoustic structure interaction coupling, multiphysics coupling, to model the vibrations out from the piezoelectric material that basically generates the sound in the fluid domain and propagates outward. So this model demonstrates you the concept of multi-method or sub-modeling approach, where you have modeled the transducer in detail in the finite element method, And you have placed this transducer on this car structure, and you analyze the propagation of sound over a very large distance using the ray tracing approach. So moving on, next we will move into the category of modeling car cabin acoustics. So we'll start with a user story here from Harman International. So they model infotainment systems that offers personalized listening experience for luxury vehicles. So the team here uses physical experiments in conjunction with numerical analysis to accelerate product development by virtually tuning their systems even before creating a live prototype. So their analysis included how the stiffness of the car doors affect the car's acoustics and how sound pressure level changes based on speaker placement. So they do a speaker placement analysis as well. They also develop a library of validated simulation apps so that engineers throughout the company can use them to easily predict speaker performance in many different conditions. So apart from creating model files, COMSOL also gives you the functionality of developing app out of your model, which can be used across different domains in your industry to yeah to understand the usefulness of the product that you have developed and to get feedbacks across different domains and teams as well. Moving here to the specific example on car cabin acoustics, simulations can be used to optimize the location of speakers within the cabin. So within the simulation domain, you can define multiple sources and you can define the boundaries of the cabin in different ways. So you can use the impedance boundary condition or you can use absorption coefficient to define the boundaries of the cabin. And you can place the microphone for analysis at any of the location that is of your interest in the cabin so that we can easily extract the data at any location in the cabin. So the parts of the car interior, as I mentioned, you can design or define using impedances. And we can also use the test data to define impedances. And the impedance that you define can also be a function of frequency. And you can also use the built-in empirical models that are available within the software itself to define the impedance of several boundaries or surfaces of your car cabin. So this model has two sources. So we have a mid woofer here and we have a tweeter here. So we are not modeling these sources in full detail, but we will simplify them and model them as equivalent circuits. And then further you can couple the electrical circuit model to the finite element model of this acoustic problem using a feature in COMSOL which is called the lumped speaker boundary condition. So when working with lumped speaker boundary condition, we configure the loudspeaker using the electrical circuit analogy. So you can have an electrical circuit comprising of voice coil and also the mechanical components. You can use the electrical circuit to represent the loudspeaker as a spring mass damper system. So that is how it is modeled in the specific example. So the tweeter, the mid-woofer and the tweeter, they both are modeled using electrical circuit analogy. So then we configure this electrical circuit so we configure using the small signal parameters. Then we connect the electrical circuit to the full 3D CAD representation of this geometry. And further we calculate the acoustics within that full CAD geometry. So here this mid woofer and this tweeter, they are modeled as different electrical circuits. And then we connect this electrical circuit to the finite element model using the lumped speaker boundary condition. So yeah, when we work at very high frequencies. The meshing requirements are high because we need to resolve the waves when we deal with medium to very large scale geometries. And here is where we usually switch to ray tracing approach. So this model shows how to model the car cabin acoustics using a hybrid FEM ray approach. So in this example, a high fidelity model of the loudspeaker driver is modeled. And then the near field solutions here are computed using the frequency domain using finite element method. And this is further coupled to large scale simulation where we use ray tracing approach. The coupling between the finite element model and the ray tracing is done on a surface. So here you see the surface. And on this surface, we use the release from pressure field feature to release the near field, basically the waves as rays to further propagate through a very large system. So the complete model here is simulated using a single model, using a single graphical user interface. And this model also shows you how you can switch from a full finite element model to a ray model as we move towards very high frequency, as we also saw in the earlier example on modeling ultrasonic car parking sensor, where the sensor was modeled using finite element approach in detail, and its integration with the car, basically integration of the transducer over large platform and analysis of the sound over large distances was carried using the ray tracing approach. So the model here compares the full finite element simulation against a pure ray tracing model. So you can visualize the plot here to understand or take a call when you have to use the finite element method and where you can switch to the ray tracing approach. So the blue line here shows the frequency response from ray tracing, and the dotted red line shows the FEM acoustic solution, basically finite element method model. At low frequency, it shows that you need to use the solution from the full wave method, whereas at high frequency, you can switch to the ray tracing approach to accelerate the simulation time. So next we have again the car cabin acoustics analyzed in time domain. So this model studies the transient response to an emitted Gaussian modulated harmonic signal solved with pressure acoustic time explicit physics interface. So the frequency dependent impedance condition of your seats, carpet and roofs are included using the general local reacting option, basically impedance option that is available. So which allows you to solve the time domain model where you can have the impedance still to be a function of frequency. And here the input data is fitted using the partial fraction fit. And the model here is solved using the accelerated solver formulation that can be run on a GPU platform. So here the slide shows the GPU performance for that particular model. So here this model had solved 49 degrees of freedom, and it solved for 30 periods for 1000 hertz pulse. On a modern GPU, the simulation is done in 1.5 hours, 1.5 hours, whereas the same model solved for 19 hours without GPU in a cluster platform. So this is a very great speed up. So from COMSOL 6.4 version onward, so you have GPU acceleration across all the physics. And yeah, now the GPU acceleration, which was earlier available for frequency domain physics, is now available for time domain and across all physics as well. So next, we will go through a demo session on modeling automotive mufflers and analyzing the transmission loss characteristics of automotive mufflers or automotive exhaust system. So now, at this point of time, I would be switching to COMSOL simulation software platform. So here, what you see in this screen here is COMSOL simulation software. So to quickly give you the introduction to the GUI, towards the left, what you see is the model builder window. And at the top, you have the top ribbon tab. Both the model builder window and the top ribbon tab, they are going to guide you through the modeling workflow. And any option or feature that you choose in the model builder window or the top ribbon tab, the appropriate setting appears here in the settings window. And towards the right, you have the graphics window. And at the bottom, you have the information window, which houses the progress information of your simulation or the log files or the log information. Or if you are plotting any results in the form of table, they also go under the information window. So the modeling workflow in COMSOL is like you start with defining parameters. It can be parameters, input parameters for your physics, or it can be the geometrical parameters to parameterize the geometry. So once you define the parameters, next you draw the geometry. So you have the geometry node where you can right click the geometry node and draw the geometry in COMSOL environment itself using various geometry primitives, or you can use the import option to import 3D CAD files, and you can import the geometry and work with the geometry to set up the physics. So you can choose the geometry node here in the model builder window or from the top ribbon tab. So we have the parameters. Next you define the geometry, and once you have the geometry, you assign materials to your geometry, and after assigning the material, you add physics or you start setting up the physics. And it is quite easy and straightforward to add physics. Say, if I want to add to this particular example further a fluid flow physics to couple flow as well. So then I can add a flow physics or any other physics that is required by clicking physics and add physics option. So once you add the required physics, you can add the multiphysics coupling. So once you add 2 or more physics, so COMSOL will suggest you the possible multiphysics coupling once you right click the multiphysics node, and you can add the multiphysics coupling that you require to capture. So once that is done, you mesh your geometry based on your physics. And there are 2 types of meshing, physics control and user control mesh. The physics control is the automated mesh feature. And once you mesh the geometry, so next you set up the study. There are various types of study. And for acoustics, so primarily you use the frequency domain study and time domain study. Yeah, and you also have eigenfrequency analysis as well in case if you want to understand the structural modes of your vibrating system. So you set up the study and you click compute button, then you would have the results, and you can visualize the results in the graphics window or in the form of table or plot. So this is the modeling workflow in COMSOL, so which is guided by this model builder window or the top ribbon tab. So moving to this particular model, so here we have 2 parameters node. So the first parameter node describes the parameters that are required for the physics. Basically the input parameters that are required for the physics and the frequency of operation. And the second parameter node is added to parameterize the geometry. So then we have the geometry completely drawn in COMSOL environment. Then we start assigning the materials. So we have taken this example of absorptive muffler to which basically describes the pressure wave propagation in a muffler for internal combustion engine. So the approach used here is generally applicable to any of the problems where you want to analyze the damping of the propagating pressure waves, as well as determining the transmission properties of a given system. So for any of the automotive exhaust system, mufflers, diesel particulate filters, so this would be more of a relevant model. And this model also shows you how to analyze both inductive and resistive damping in pressure acoustics. And the main output that we are trying to analyze here is the transmission loss characteristics of this muffler. And we are also going to couple this acoustic model with structural mechanics physics to account for acoustic structure interaction, which can affect the transmission loss characteristics. So when you model a full vibroacoustic model of your muffler or exhaust system, then is where you would get the full idea of the transmission loss characteristics, because the vibrations, external vibrations or sound induced vibrations, they are also going to play a major role in determining the transmission loss characteristics or how your noise is getting affected through your muffler system. So moving on to this specific geometry. So here you have a 24-liter resonator chamber with a section of centered exhaust pipe included at each of the end. And this model is also lined here with, so you see a lining here as well, right? So this is almost a 15 mm of absorbing glass wool. So the exhaust fumes, they enter through the left pipe and they exit through the right pipe. So in real muffler systems, the main effect of acoustic structure interaction is probably due to the elastic vibration sources that arise from the vibrations in the full exhaust system. So in this particular model, the vibrations are basically induced only by the pressure waves in the air that is basically inside the muffler. And further to this model, you can add external structural sources as well, which can be source of vibration apart from the sound induced vibration. So which you can do by specifying a deformation or velocity on a specific edge or points or boundaries in the structure. So that's about this particular model or its geometry. And moving on to the material. So here we have air that is modeled inside this chamber. And you have steel to model the casing of this muffler. And moving on to the physics, we have added two physics here. One is pressure acoustic frequency domain physics. So as we are solving this problem in frequency domain or plotting the transmission loss characteristics over wide range of frequencies. And we also have shell physics here to understand basically the vibrations that are induced because of noise. And you can also add external vibration sources as well that can affect the transmission loss characteristics. And to set up the pressure acoustics problem here, so you need to specify what is the input for your sound and where is the boundary where your sound is exiting. Okay. So we have port boundary conditions to model the inlet and outlet of the muffler. So at the inlet, you specify the sound magnitude that is at the inlet or input of this muffler. And next, you have this acoustics domain or feature that is included here in this model to model the porous domain, or here it basically the glass wool or the liner. The absorbing glass wool here is modeled as acoustics domain. So here we use an equivalent fluid model for the porous domain where your losses are modeled in a homogenized way. So the Delaney-Basley-Mickey model is used here, which is the default model to model the porous domain. And you also have several other models as well, which can be selected based on your application or situation. Yeah. So here, the speed of sound and density are included from the material, and the flow resistivity of glass wool is modeled here using the Delaney-Basley model. Yeah. So this is about the pressure acoustic physics. And moving to shell physics. So here, these are the default nodes. The first three nodes that you see with all these physics are the default nodes. The first node talks about the equation that we solve, and the default boundary condition is the second node. Yeah. So here, when we look at this shell physics, so the thickness of the steel, the outermost steel structure of your muffler system. So that is around 1 mm. The thickness is defined here for your shell structure. And also, you also have straps here. We have also modeled straps. So the straps here on this muffler, the thickness is around 3 mm here. So then you also have fixed constraints. So the straps are fixed at these boundaries. So, and we have applied fixed constraint boundary condition here. And the port as well, the edges of the port are also fixed. So yeah, that is about that. These are the two physics that is of interest here, and you can keep adding physics. So just in case if you want to couple flow with this, so you can add flow physics as well further to the system. And moving to the multiphysics node, so we have added pressure acoustic physics and shell physics to capture vibroacoustics. And I need to tell, we need to couple pressure acoustic to structural mechanics. So then you right click the multiphysics coupling. COMSOL will suggest you the possible multiphysics coupling. So here acoustic structure boundary is the multiphysics coupling that is added to capture the acoustic structure interaction. Yeah. After adding that, so then you mesh the geometry. And once you mesh the geometry, so we need to set up the study. So here you can see 3 types of studies that are performed. First is the pressure acoustic study in frequency domain, where we do not include the shell physics or we do not model the acoustic structure interaction. So you model only the pure acoustic problem and you plot the transmission loss characteristics of the pure acoustic propagation problem, wave propagation problem inside this muffler geometry without including external vibrations or sound induced vibrations are not modeled. So you can see the selection box or the check box here, only pressure acoustic study is performed. And the second study is the model where we couple pressure acoustics with shell physics and model acoustic structure interaction and understand how the transmission loss characteristics are further affected by coupling acoustic structure interaction. And at the end, you also have an eigenfrequency study in case if you want to analyze the eigenmodes of this particular structure from pure structural mechanics point of view. So here at the third study, only shell physics is selected here to analyze the structural modes and how the structural modes highly correlates with the peaks that you see in the transmission loss characteristics. To compare that, an eigenfrequency analysis with structural mechanics physics is also added. So now I think we will go move on and check the results out from the simulation. So once you set up any of the study, you just need to click this compute button and COMSOL will start the simulation. So yeah, in the interest of time, so we will go and visualize the results. So by default, so when you install acoustic physics, so you would have these plots. So the total acoustic pressure plotted on your structure, and if you are modeling surrounding air domain, so you can model the total acoustic pressure on the domains that you have included in the geometry. And you can also visualize it in dB scale or in log scale, sound pressure level. Yeah, and yeah, this is just a visualization of the same total acoustic pressure as isosurfaces. So this is a pure pressure acoustic study. And the second study was about acoustic structure interaction. So you can see again the total acoustic pressure plotted on this particular structure where vibroacoustics is modeled. And you can also visualize basically the concentration of the stresses or the maximum displacement or deformation the structure can undergo. So currently this model includes only the vibration that is induced only from the sound source, but yeah, further you can integrate external vibrations as well. So you can visualize the displacement magnitude and where the maximum displacements are concentrated as well. And further, you can visualize the transmission loss characteristics. Yeah. So you can plot the transmission loss characteristics here. So here, yeah, you can see a stronger effect on the transmission loss if there are structural vibration sources. So strong acoustics sources may appear again at the muffler walls as well. So the structural sources are not accounted here, but you can account for the structural sources as well. Okay. So we have used the octave band plot feature to plot this transmission loss characteristics. And here you can see the variations in results between without integration with shell versus integration with cell. And you can see these peaks in the shell. And you can easily correlate these peaks with the eigenmodes that you have computed using structural mechanics study. Say one of these peaks, which is like 204 or 205 hertz. So when we go to the mode shape analysis, this is which is basically the plots from eigenfrequency analysis. So you can see various eigenmodes. So one of them is like 205 hertz. And all the peaks that you visualize here in acoustic structure interaction study, so they correlate with your eigenmodes, and that's why eigenfrequency analysis is also included in this model. So you can also plot the transmission loss in 1/3 octave scale as well. So this is about this demo model. So moving further, before moving to the end of the session and taking the questions, so I would like to answer another poll question. So where we would like to understand whether you are interested in connecting with the COMSOL representative further, or you would like to try out COMSOL for any of your upcoming projects, or is it both of above, or it is none of the above and you would like to explore COMSOL at your own interest. So I would request you all to take time to answer this poll question that you have in your mind ready for our Q&A session as well. So thank you everyone for showing up interest in this particular session on modeling automotive acoustics application using COMSOL multiphysics. And the poll is here open to answer the question. So kindly take time to answer this poll question. You can keep your questions ready as well. Thank you for answering that poll question. Yeah, thank you everyone. As I mentioned, for showing interest in this session. And COMSOL Multiphysics provides you a very great platform to model multiphysics applications with in line with modeling automotive acoustic applications. And you have built-in multiphysics coupling, and you have the flexibility to establish your own multiphysics couplings as well, or to come up with a multiphysics model. And I would request you to go through COMSOL website further to understand COMSOL product portfolio and what are the various areas that COMSOL can address. And you can go through other online resources where you can find various application library models online as well that relates more with your application area of interest. And we also have further resources like blogs and learning center pages to get to know about COMSOL simulation software in a more detailed way. Thank you, everyone. So you can post your poll questions. You can post your questions that you have in your mind.
Thank you so much, Ms. Kavita, for that informative and engaging presentation. We are sure our audience has gained valuable insights to automotive acoustics and multiphysics simulation using COMSOL. Let's now move to the Q&A sessions. We have received some thoughtful questions for our participants, so let's dive right in. We've received first question. The first question is, can we model perforates in automotive mufflers?
Yeah. Yes, definitely you can model perforates in automotive mufflers or your exhaust system. So you can model the perforates in detail. So the holes or the perforates can be modeled in detail explicitly in your geometry through your geometry, or you can use perforated boundary condition feature that we already have within COMSOL simulation tool. So to model the perforates for your exhaust system or muffler systems. So
Okay.
when you use the built-in feature of modeling the perforates, so then you can avoid modeling the holes or perforates in detail, so that we avoid concentration of mesh over very small holes or perforates.
Thank you so much for the answer. Our second question is, can we plot the radiated sound pressure fields over the far distances?
Yeah. Yes. So regarding radiation characteristics out from your vibrating device or for acoustic wave propagation, um, for scattering analysis or radiation problems. So you can model acoustic total sound pressure level, so SPL characteristics over very large distances as well. So COMSOL has exterior field calculation feature where you can add that particular feature to calculate the sound propagation. So if I have a very small system and you want to visualize or you want to understand what would be the sound pressure level over very large distances, very large scales, so you can use that particular feature to calculate the far field results from your near field sound pressure levels.
Thank you so much for the answer. We have one last question, which is, can we couple the flow with acoustics in automotive exhaust system?
Yes, definitely. So like in the last model that we saw, so we have various ways in which you can couple acoustics with flow physics as well. So in particular, like with regards to the last model that we discussed, if it is for exhaust system or muffler, so you can solve pressure acoustics um, in the presence of a stationary isothermal or non-isothermal flow medium in the background. So you have specific formulations to model that, or you can couple with a flow physics as well. So you can add fluid flow physics, turbulent flow models. You can model the flow physics and couple the fluid as the background medium for your pressure acoustic physics.
Thank you, Ms. Kavita, for your detailed and enlightening responses. A heartfelt thank you to our audience for your active participation and excellent questions. As we conclude today's session, we would once again like to thank COMSOL for their unwavering support and all of you for joining us and marking this webinar a success. We look forward to welcoming you again soon to another engaging and knowledge-rich session. Thank you so much. Have a great day ahead.
Yeah. Thank you, everyone.